Hey, good morning, everybody. We're going to keep looking through first and second derivatives and curve sketching. So what I have for you today is notes for section 4.4 on the second day. I've got one example to kind of help you through the Delta math assignments. If you get stuck, no problem, take a screenshot, send it to me, and we'll work through it. On the top of our notes, I have a picture that I included in yesterday's notes, which shows the increasing, the decreasing, the concave up, and the concave down. So as a reminder, both of these curves are increasing. Both of these curves are decreasing. The two curves on the top are concave up, and the two curves on the bottom are concave down. So the really cool thing about this little chart is all functions, all curves, all pictures everywhere are only made up of those four. And it's just how you put those four pieces together determines what the shape of that actual function looks like. So we are going to kind of figure out, well, how do we do that? So today we're going to look at little pieces. And then when we look at section 4.5, we're going to put it all together and sketch the actual curve. So what we're going to do, and this is only one example, is given the following function, determine all intervals on which f is both decreasing and concave down. So decreasing and concave down. So for this particular question, and that's how Delta Math is going to ask it, decreasing concave down is this curve. So we want to know which part has that curve. For the process today, I'll show you how to get all four of those pieces. If all four are applicable, maybe it's only one or two. But Delta Math is only asking for one piece at a time. So given the following function, determine all intervals where f is both decreasing and concave down. Decreasing, we know, comes from the first derivative, and concave down comes from the second derivative. So today is our opportunity to put together all of that stuff that we've been talking about over the last week or so. So we're going to start with the first derivative. F prime of x is equal to negative 5 x to the fourth minus 20 x cubed. And we need to set that first derivative equal to 0. Why do we do that? We're going to look for the critical points, and those critical points help us figure out the intervals where we are increasing and decreasing. Oops, I just took a derivative again. No worries, erase that. So 20x cubed, my 4 got deleted. So now that I've set this equal to 0, I'm going to factor out as much as I can. What can I factor? A negative 5x cubed. So here's x plus 4. So what is x equal to? X is equal to 3. No, it's not. I saw that exponent. It's early, can you tell? X is equal to 0 for this piece. And then we are looking at negative 4 for the next piece. So these are the critical points. That's great and all, but I need to know increasing, decreasing. So this is where we put it on a number line. Here's negative 4 and 0. And again, we want to choose those in-between values. We want to substitute them into the first derivative to see if we get positive or negative. I kind of like that factored version again, but you can use any of the above. You can use your calculator, it doesn't matter. If I put a negative 5 cubed is going to be a negative number, and a negative times a negative is a positive. If I put negative 5 in this quantity, it's a negative. So a positive times a negative means we have a negative. If I choose negative 2 here is cubed. So that's a negative. Negative 5 times a negative number is a positive. A negative 2 in here gives me a positive. So a positive times a positive is a positive. And then if I choose, say, a 7, that's bigger than 0. You could do 1, anything, but I went with 7. 7 cubed is a positive. Negative 5 times a positive is negative. 7 plus 4 is a positive. So all of this becomes a negative. Okay, so that means that we are increasing from negative 4 to 0. That's where it's positive. And we are decreasing on those negative intervals. So negative infinity to negative 4 and 0 to infinity. Awesome. All that is the first derivative piece. So second derivative, what do we got to do? I used a lot of space here, didn't I, today? Second derivative is going to be, let me go back and look, negative 20x to the third and then the derivative of the second piece is negative 60x squared. So the process looks very similar to the process in the first derivative, but now we're just using the second derivative. So we have the second derivative, set it equal to 0. I'm going to factor out a negative 20x squared. And if I do that, I've got x plus 3. My solutions for x are going to be 0 and negative 3. Now, first derivative gave us critical points. Second derivative gives us inflection points. Again, we'll do the number line. We want to make sure they're in numeric order. And the values that I put in are going to go into the second derivative. Again, I like that factored version. It just works best for me. But if you're using a calculator, it really doesn't matter. So if I put a negative 4 in here, this gives me a positive. So negative times a positive is a negative. A negative 4 here is a negative. So negative times a negative gives me a positive. If I choose a negative 2 for this interval, over here I wind up with a negative. Over here I wind up with a positive. Did I do that right? Nope, I didn't. All right, negative 2. Negative 2 here is squared, so that's positive. Negative 20 times a positive is a negative. Negative 2 in here is a positive. So negative times a positive is a negative. There we go. And over here at the 0, a number larger than 0 is 1. So 1 squared is 1. Negative 20 times 1 is a negative. 1 plus 3 is a 4. So a negative times a positive is a negative. Hello. All right, there we go. So we can say that we are concave up from negative infinity to negative 3. We are concave down between negative 3 and 0. Now you want to stop at 0, include that break, union 0 to infinity. Great. So we figured out increasing, we figured out decreasing, we figured out concave up and concave down. Let's go back to the original question. Where are we decreasing and concave down? Delta Math explains this a little bit differently. If we were in class, I'd have a couple worksheets for practice with this, but I always put them together in a table. It's a little tricky to make the table the first time, but I think it simplifies the process later on. So we want concave down and decreasing, decreasing, concave down. So I need to remember these points. We're going to remember a negative 4 and a 0, and negative 3 and 0. So here's what my table looks like. We've got negative 4, negative 3, and 0. And I need to scooch those over just a little bit. Hold, please. Just gonna slide those there. There are lots of drawing apps out there. I downloaded Notability. That's what I'm using on recommendation from a teacher. And goodness knows I'm still learning it, but there's some kind of cool things. Okay. So in my table, I'm going to have information about the first derivative and the second derivative. Basically, my table represents both number lines. So if I come up here and we talk about the first derivative information. Well, the first derivative went negative, then positive, then negative. And the critical points were at negative 4 and 0. So that's what I'm going to fill into my table. Negative 4 and 0 were my critical points. So those had a value of 0. The first derivative had a value of 0. And then by my number line, it went negative, positive, negative. Negative, positive, all those positives for all those boxes, and a negative. Now for the second derivative, same idea. My inflection points were at -3 and 0. And then the values for my number line, well, it was positive anywhere to the left of -3. And it was negative between -3 and 0. And it was negative to the right of 0. Again, Delta Math doesn't do this. This is a Mrs. Charnley thing. And you see it in some textbooks otherwise. I did not invent it by any means. So then we have to look at what happens when we put it all together. So remember, the first derivative talks about increasing, decreasing. The second derivative talks about concave up and concave down. What I don't have is a picture of that table in front of me. And if we were all together, I'd say, hey, you know, which figure is it, A, B, C, or D? We'd put it all together. So I'm kind of referring to this guy right here. Decreasing concave up, increasing concave up, decreasing concave down, increasing concave down. So if you can kind of look at the top of your paper, the front of your paper, which I can't see while I'm scrolling here, you can follow along with me. So the first piece is decreasing concave up. That decreasing concave up curve looks like this. Don't worry about what's happening at the actual critical and inflection points, just let that go. The next piece is increasing concave up. So this is the graph of increasing concave up. -3, don't worry about that right now. All the important stuff is in the in-between values. The next region is increasing concave down. So increasing concave down looks like this. And the last region is decreasing concave down and looks like this. So again, back to that original question. Where are we decreasing concave down? So decreasing concave down, decreasing is negative first derivative and negative second derivative. Decreasing concave down. So I'm looking for double negatives here. That's not it. The second region is not it. The third region is not it, but the fourth region is decreasing concave down. So to answer the question, we are decreasing concave down between 0 and infinity. So in Delta Math, they're not looking for the whole table. We're going to use that table to help us graph next week. They just want to know the specific region. Where is it decreasing concave down, or increasing concave down, or increasing concave up, or decreasing concave up, any one of those four possibilities. So they just want to know that one interval, where is that happening? And you can always check your work with a calculator. That's easy enough to do. So let's see if I can remember this here. Negative x to the 5th minus 5x to the 4th. Negative x to the 5th minus 5x to the 4th. Did I remember it okay? Yay. Y equals, that piece is already there. All right. Well, that's a super steep graph. Let's make this negative 50 to 50. See if we can get that on there. Oh, that's super stretched down. Negative 300. Hold, please. This is Desmos. I think you guys have that on your iPads. All right, so if I stretch, I can't stretch that way. There we go. All right, if you look at this graph, it's a little bit funky, but to the left, this is my decreasing concave up. And then it switches to increasing concave up. And somewhere in here is our inflection point at -3. It should be right there. If I can graph on. -3, there's our inflection point. So it switches to concave down. And then this whole region is concave down, increasing, concave down, increasing, concave down, increasing. And then it switches to concave down, decreasing. And that's what we had said, from 0 to infinity. So decreasing concave up, And then we've got increasing concave up, increasing concave down, and decreasing concave down. So those are those 4 regions that put together any function in the world, which is kind of cool. So great job. Try those 6 problems for section 4.4 day 2 that are in Delta Math. You're welcome to watch the videos for extra help if that works for you. You can rewatch this video if you want to, send me screenshots when you're stuck, but I do appreciate you trying. I'm just trying to help you out for your next math class. So good job, keep it up. Let me know when you get stuck. There's still several of you I haven't heard from at all. So please, please, please reach out if you've been stuck. See ya.